Here's the problem I see all the time. A reaction that works beautifully in a beaker turns chaotic in a plant. Heat that quietly dissipated in the lab now spikes. Mixing that looked fine becomes stratified. Selectivity nosedives. Byproducts creep up. Your simple separation train turns into an energy hog. The challenge isn't just making a reaction happen. It's making it happen predictably, safely, and profitably, every hour of every day. So, here's the process I use to design reactors and the unit operations around them. Step 1. Define the objective in numbers. Conversion, selectivity, throughput, uptime, allowable impurity levels. Then characterize the chemistry, kinetics, heat of reaction, phase behavior, catalyst quirks, deactivation or poisoning. Next, pick the reactor type that fits the physics, not the fantasy. Batch or semi-batch for flexibility and tight dosing control. CSTRs, robust mixing and temperature control. PFRs, high throughput and narrow residence time. Loop or trickle bed for gas, liquid, or catalytic needs. I match that choice to mixing and heat removal demands because heat transfer usually sets the limit, not stoichiometry. If the reaction is exothermic, I design heat duty first. Jackets, coils, external exchangers, quench feeds. If it's mass transfer limited, I design interfacial area and shear before I chase catalyst loading. Control strategy comes next. Feed rates, temperature, pressure, composition, staged feeding to flatten heat release. Cascade temperature control, pressure relief sizing from credible worst cases, not hopes. Relief systems, inerting, interlocks built in, not bolted on. Around the reactor, I design the separations to close the loop. Distillation where volatility helps. Liquid-liquid extraction when it doesn't. Membranes to save energy. Crystallization for purity. Adsorption to polish. Recycles get purges to stop inert buildup. I pinch integrate heat so hot streams pay for cold ones. Utilities matter. Cooling capacity at summer worst case. Steam curves. Power quality for drives. Before steel, I simulate a steady-state model to map operating windows, then a dynamic model to test startups, trips, and transitions. If the model survives abuse, I build a pilot or demo skid to find the gremlins, fouling, foaming, sensor drift. Commissioning plans force discipline, water runs, inert runs, then live runs with procedures that operators actually helped write. Here's the payoff. When I follow this path, plants hit spec faster, burn less energy, and stay online longer. An exotherm becomes a heat source for distillation. A tricky impurity becomes a recoverable co-product. Uptime climbs because the process is controllable, not fragile. And scale doesn't feel scary, it feels engineered. Designing reactors and unit operations isn't magic. It's problem, process, payoff. Do the physics first, and the economics follow.